Harrison Insight.
Welcome back to the deep dive. Today, we're undertaking a really critical and high-stakes investigation. We're looking at the core mechanics of heart failure.
We are. And it's a condition that's defined by this stunning biological paradox, which is really what we're here to unpack.
Exactly. That's our mission for this deep dive. We're moving past just the simple diagnosis.
Yeah, we're getting into the underlying pathophysiology. I mean, our sources detail this relentless, self-perpetuating problem. Scientists call it the vicious cycle for a very good reason.
And the real tragedy of it is that the body's own attempts to compensate these highly evolved fixes.
They're precisely the mechanisms that accelerate the destruction. The body's solution becomes the problem.
So we're tracing that self-destructive loop. Our sources give us a really deep look at the chemical, the mechanical, and the systemic changes that drive all this.
Right. And to map it out, we have to look at two huge overlapping components. First, there's the local damage happening right inside the heart structure. That's what we call ventricular remodel.
Okay, the local part.
And second, there's the body-wide response.
Yeah.
The alarm system, the central nervous system and the hormonal cascade. That's neurohormonal activation. And they are locked in a devastating feedback loop.
Okay, so let's start with the mechanical stress, the initial insult. I want you to just visualize the heart under continuous, unending strain. What are the chronic physical loads that kick this whole thing off?
Well, the initial stimuli are rooted in basic physics, really, specifically chronic hemodynamic stimuli.
Hemodynamics, so blood movement.
Exactly. You have to think of it as a persistent, excessive workload being placed on the muscle fibers. This shows up as two key forces, pressure overload and volume overload.
Okay, pressure overload makes intuitive sense. That's like high blood pressure, right? The heart is straining against this intense resistance with every single beat.
Right, but what about volume overload? What does that look like?
Well, volume overload is literally having too much fluid in the system, maybe because of damaged valves or kidney issues. The heart chamber is just constantly overstretched. It has to pump an unsustainable amount of blood.
And regardless of the trigger pressure or volume, this chronic strain leads to one devastating consequence for the heart tissue.
Which is?
It dramatically increases the myocardial wall stress.
No.
And you have to think of the heart wall not as some concrete bunker, but more like an exquisitely specialized elastic rubber band. And when you continuously force that rubber band to stretch and snap under impossible resistance, that stress starts triggering a complex chemical alarm system inside the muscle cells themselves.
So the mechanical strain is instantly converted into a molecular crisis.
A molecular and chemical crisis.
Precisely.
That high physical stress acts as a catalyst for a really detrimental cascade.
Right.
You see the release of inflammatory cytokines, signaling peptides, neuroendocrine signals.
Wow.
And crucially, you also see a massive, sustained increase in oxidative stress.
Which is basically cellular rust.
It's cellular rust. The tissue is stressed, it's chemically inflamed, and it's being bombarded by free radicals.
So how does the heart muscle, the myocardium, how does it try to cope with this hostile environment? Does it try to bulk up, get stronger?
It does try, and those are the initial adaptive changes. But the attempt very quickly crosses the line into what we call maladaptive changes. The physical expansion hypertrophy, it helps at first, but the actual structure of the muscle fibers changes for the worse.
And this is where it gets really bizarre. The sources point out that the stressed heart starts, reverting to ancient blueprints?
That's a perfect way to put it. It's like the adult cell decides, I can't do this job, I'm going back to the factory settings.
So what does that mean chemically?
It means the re-expression of fetal contractile proteins and changes in crucial calcium-handling proteins. These are structures the heart used when it was developing in the womb, under very low resistance conditions.
But in an adult, that's a disaster.
It's a disaster. Their re-expression severely impairs the fundamental mechanics of the heart.
Impairs it how? What's the physical result?
The main result is just diminished function. These proteins inhibit the efficient binding and release of calcium, which is the spark for muscle movement. So the heart can't contract powerfully or relax fully.
It becomes inefficient.
Rigid.
A much, much weaker pump. And for the individual muscle cells, the myocytes, that can't cope with all this stress.
What happens to them?
They're triggered to undergo programmed cell death, apoptosis. You are literally shedding functional cells and replacing them with nothing, or worse, with scar tissue.
And that cell loss, combined with the poor function of the cells that are left, that just circles right back to putting more stress on the remaining tissue, it seems inescapable.
It is the definition of the cycle. The net result is profound pump impairment. A weaker pump means higher pressures and volumes inside the chambers, which means increased wall stress.
And that restarts the whole degenerative process, a localized spiral of destruction.
Exactly.
That's the mechanical part. Now let's pivot. Let's see how the body's centralized alarm system responds, because the heart is struggling locally, but the rest of the body has to be sensing a massive systemic problem. It is. When the heart fails mechanically, its output drops. And this is the transition point from mechanical failure to systemic disaster.
Yeah.
The entire neurohormonal cascade kicks off with one simple trigger: decreased cardiac output.
The moment of panic. The brain realizes the circulatory system is on the verge of failing. How does it register that so quickly?
Instantly, via the baroreceptors. These are high-pressure sensors located in key areas: the left ventricle, the carotid sinus, the aortic arch. They're constantly monitoring pressure.
Okay.
So when the heart's output drops, the pressure they sense suddenly falls. They're effectively unloaded.
So if they usually sense high pressure and tell the body to relax, sensing low pressure must trigger the absolute opposite.
The absolute opposite. The unloading sends a panic signal to the central nervous system. This causes a rapid reduction in the body's calming system, the parasympathetic tone.
Which opens the floodgates.
It opens the floodgates for a generalized increase in the efferent sympathetic tone. The fight-or-flight system takes complete command.
Okay, so the sympathetic nervous system is in overdrive. It needs to maintain pressure right now. So it starts dumping hormones. Which ones are first on the scene?
One of the immediate responders is arginine vasopressin, often just called ADH.
Vasopressin, that's famous for regulating water, but in heart failure, it takes on a dual role, doesn't it?
It does. It has two functions, both aimed at stabilizing blood pressure. First, it's a powerful, system-wide vasoconstrictor. It squeezes the peripheral blood vessels to raise pressure instantly.
And the second function?
It acts on the kidney, forcing it to reabsorb free water. You retain fluid, which increases your total blood volume.
Brilliant for the short term. Pressure and volume are back up. But that sympathetic activation is widespread, isn't it? It's reaching deep into the organs.
That's the problem. This sustained signaling activates sympathetic nerves everywhere, to the heart itself, telling it to beat faster and harder, to the peripheral vasculature, making resistance even higher, and crucially, to the kidneys.
And that's what sets the stage for the most famous part of this whole response.
The RAS system.
The renin-angiotensin-aldosterone system. So sympathetic signals hit the kidney, which is already scrambling, and the immediate consequences.
The immediate consequence is the release of renin. Renin kicks off the cascade, leading to hugely increased circulating levels of angiotensin II and aldosterone. This is the fully activated RAAS system.
And its long-term effects, these are the key accelerators of the damage.
They are. And we can break it down into 5 critical actions that just keep feeding that cycle.
Okay, let's walk through them. What's number 1?
Number 1, angiotensin II and aldosterone promote massive salt and water retention. This dramatically increases the circulating blood volume. Remember that volume overload we talked about at the start?
The system is now actively manufacturing it.
It's manufacturing it. Then number 2 is intense peripheral vasoconstriction. Angiotensin II is one of the most powerful constrictors we know of. This raises the resistance the struggling heart has to pump against.
A pressure overload. So the systemic response is chemically reinforcing the exact mechanical stresses that started the failure in the first place.
Exactly. But the damage doesn't stop there. Angiotensin II also does direct damage to the heart muscle.
Which is number 3?
Number 3, it contributes heavily to myocyte hypertrophy. That's the pathological, damaging enlargement of the heart muscle cells.
And it also contributes to the loss of cells, right?
Correct. That's number 4. It triggers further cell death, adding to the apoptosis that was already destroyed by the mechanical stress.
So the body is chemically instructing its own essential muscle tissue to just die off.
And finally, number 5, which ties everything back to remodeling, is myocardial fibrosis.
The scarring.
The scarring. It's the laying down of stiff connective scar tissue. You're replacing high-performance muscle fibers with dense, non-functional cement.
Okay. So this brings us to the critical paradox, the so what. We've mapped out this incredible integrated system that kicks in when the heart fails. But if every single action it takes ultimately reinforces the cycle of destruction, why does the body do this?
Because evolutionarily, the immediate priority trumps everything. These neurohormonal mechanisms are all about short-term adaptation. Survival now. In a moment of crisis, when blood pressure is dropping, the primary goal is just maintenance. Keep the lights on for the next few hours. You need volume and pressure now, regardless of what damage it causes 3 months from now.
So it maintains circulation today by generating accelerated heart failure tomorrow.
That is the staggering trade-off the body is making. And the cost is severe end organ changes. The systemic alarm system provides the exact chemical fuel that drives the local mechanical breakdown.
The structural damage reinforces the functional failure.
And the functional failure demands more systemic activation.
It truly is a vicious, self-perpetuating loop, driven by the body's brilliant but tragically self-destructive attempt to just maintain basic circulation.
And what's really crucial for you to take away is that connection. The sustained neurohormonal activation, that chemical alarm, is directly responsible for the fibrosis, the hypertrophy, the cell loss. The systemic panic feeds the local irreversible destruction.
Right. Food for thought, then. We've seen how maintaining blood pressure with aggressive vasoconstriction and fluid retention is the body's key short-term strategy. It gets you through the day. But this raises an important question for you, the listener, to think about. If the goal is just temporary maintenance, how does the sheer duration of the sustained pressure and chronic hormonal overdrive affect the ultimate point of no return? What happens when short-term becomes chronic over months or years, and the heart is permanently poisoned by its own rescue attempt?
It's the essential question that drives almost all of the modern pharmacological management of heart failure, blocking these very pathways to give the heart a chance.
Thank you for joining us for this deep dive.